So first, we record the complex numbers. We have learned this before. So the complex numbers. Previously, we have this z equals x plus I, y. We will call x the real part. And y the imaginary part. In this setting, we assume that both x and y are real numbers. Okay. Let me check with you have the following numbers. Okay, Eric, what's the real part? What's the imaginary part?
The real part's 2 and the imaginary part's 3i.
Okay, so that's the, maybe we should emphasize the imaginary part is only y, not iy. So both imaginary part and real part are both real numbers. For this one, we say the imaginary part is 3, not 3i. I is the imaginary unit. Okay. X equals 2, y equals 3. Second one. Okay, Amy, what's the real and imaginary part of this complex number?
Is it still 3 or yeah?
What's the real part? What's the imaginary part?
The real part is 2 and then the imaginary part is it still 3? No, because like I times I is gonna be -1 and then
Okay.
so it's oh wait, so it's
Uh,
3i times -1, so is it like -3? I'm a
okay,
little
so you
confused.
notice the trick over there. So here, to find the real and imaginary part, we must simplify it first. Because okay, so this is incorrect. Some may say 3i is also incorrect. How to find the real and imaginary part? We need to simplify this. Okay, Amy, how do you simplify this?
Um, you can like multiply them.
Okay, so we
Yeah,
have 3i squared. And then we know I squared is
-1.
-1. So this is 2 minus 3. Okay, okay. Now let's see what's the real and the imaginary part of this complex number. Okay, Amy.
Um, the real part is -1
Mm-hmm.
and the imaginary part is I don't know.
So there is no imaginary part, it's just 0.
Okay.
Mm-hmm. Okay, so we should be careful when we say the real part and imaginary part of a complex number. By default, they must be real numbers. Even when given in this form, we cannot say this is the imaginary part because this is not a real number. The, to find the real part, imaginary part, we have to simplify it first. get the real number, then we say, okay, so this is the real and imaginary part. Okay, and this particular form, when both parts are real, called the rectangular form. Okay. For comparison, we also introduced the polar form. Let's start with a picture. Okay. So given a complex number, we can find the real part, the imaginary part. The polar form goes this way. We find this because the modulus. Okay, the modulus in some sense the size, also norm, both works. Modulus of the complex number. And the second part is theta, the argument. Okay, now let's recall if in this right triangle, the hypotenuse is r, this is theta. How do we represent this side and these two sides? Okay, let's check. Jessica, okay, Jessica, can you find the relationship of these two sides using r and theta?
Um, well,
We
um,
have a right triangle. This side is hypotenuse. This side is angle is theta. What about this one?
wait, what is the other side?
This side, so this is x, this is y.
Uh, um, no.
Kira.
Sine theta?
Okay, so this one will be sine theta and with r. So this is y. The same way you can see x. Okay, so in the polar form, our complex number will be r cosine theta, I sine theta.
Wait, I
So
have a question.
yes.
Why is it like called the argument?
Uh, uh, so because uh, argument, sometimes we say if you give a function, because this is the variable, right? But we sometimes also the argument. This is the change. Some quantity changes called argument. It's not a good name, but it's what we used. Uh, Okay, so R the common factor we put out cosine theta I sine theta. Okay, so this is called the polar form. One step further, we have this Euler formula. Okay. Why is this formula true? That's a very difficult question. Okay, we have to wait until you go to college, you learn calculus, then you will learn why this is true. So for now, we will take this for granted. We will use this formula. With Euler's formula, we can rewrite our polar form, make it more compact. Okay. So the connection between the rectangular form and the polar form. And then the other way, we can go back and forth from rectangular form to polar form. This looks very natural, but we should be very careful. This is the first time we are dealing with complex, maybe imaginary exponent. So be careful in dealing with. Uh, One question from last week's homework is this. Okay, let's see how we find this. EI 2 pi. Okay, okay, Eric, how to find
2
this?
pi is just 180 degrees.
2 pi is, what's that?
180 degrees.
Is pi or 2 pi? 180.
Oh wait, 360 degrees.
Okay, okay.
And then theta equals to 360 is just
Mm-hmm.
cosine 2 pi plus I sine.
So what's cosine 2 pi?
That's 1.
Sine 2 pi.
0.
Okay, now let's compare it with EI 2 pi if we divide this by 2. Let's see the difference between the two expressions. It's Amy's turn. Amy, how do you find this one?
Um, sorry.
Mm.
Um, so I kind of had a little trouble with that, and I'm not sure if it's correct, but I think it's just the first one divided by 2, but I'm like not sure.
What does it mean? First one divided. You mean this one divided by 2?
Well, like no, wait, like okay, yeah, I can't, I don't know how to.
Okay, let's start with the exponent. Can you simplify this?
Yeah, so it's like I times 180.
Okay, so it simplify it. First, we get EI pi. Okay, let's apply Euler formula. What's EI pi?
Um, the,
The formula, not the result.
uh, do I remember it?
Okay, so that's the Euler formula. Let's apply Euler formula. What do you get?
Uh, cosine theta plus I sine theta.
What is theta?
Pi.
Okay,
No, wait, yeah.
okay. So what's cosine pi?
Um,
So if we draw a coordinate, pi is this way. What's cosine pi?
like 180.
Mm-hmm. Pi is 180. So cosine 180 is -1.
Mm-hmm.
Okay, and Jessica, what about this one? How do we evaluate this?
Um, uh, they're
We can
not,
start with the interior. What's the interior?
um, is a pair of I to pi.
Uh-huh. Which is 1. We
Yeah.
computed before. This is 1. 1 to the 1/2. What's this?
Wait, 1/2. Wait, no.
1 to the power. So square root of 1. What's square root of 1?
1.
Yes.
Oh, yeah.
Okay. So now we can see the difference. These two, the first one gave us -1. Second one gave us 1. So they are different. So is not. More generally, E I theta. Be very careful. In this special case, this is well defined. For the general case, this may not be even defined. Okay. Not well defined. But this always well defined. Okay. So this Euler formula, the complex ex exponent, looks very nice, very useful, but we should be very careful about this. We apply this formula only when it's applicable. So I have some message from Eric. So which one is correct? Eric, both are correct. But you should make was you right? What you wrote is kind of ambiguity over there. Eric, right? EI pi, EI 180. It's not 180, but 180 degrees. Eric, see the difference? So this is a degree, but this is the number or sometimes radian. If you forget the degree to mean something different. So this is cosine pi is -1. Eric, is this your question? No? Okay, what's your question, Eric?
Nothing.
Nothing. Okay. Okay. The next one. Okay, so we generalize the imaginary exponent a little bit. Ex plus iy. So from imaginary to complex exponent, this is defined as the product. Previously, this is not defined yet. This is the first time we define this complex exponent. This is easy. Exponential real number have done this many times. This one, Euler formula. Y the real number. Cosine y well defined, sine y well defined. This is the well defined complex number. Okay. Now we know so e to the z for any complex number. Okay. Now we know what the complex exponential is the multiplication of the exponential of the real part, exponential of this, we apply Euler formula. So more generally, we have the laws. Complex explanations. Two complex exponential. Both z and w are complex numbers. Then this is second formula e z to the nth power. Okay, but we should be very careful. This applies only when this is an integer. As I mentioned before, the formula when this is the half is incorrect. Formula when this is third or any fraction is incorrect. We can only allow integer multiple for the out. In particular, we don't have the following formula. There is no such formula for complex exponents, complex exponentials. Okay. Okay, let's just consider a special case when both z and w are 2 pi I. See what happens. Okay, I'll give you a few minutes to figure this out. When z and w are both 2 pi I, can you simplify the first one for the second one? Do we get the same result? Jessica, do the work. You can enter 1 in the chat when you are done. Okay, I have 1, 2 pi I. The first one, we substitute z and w by 2 pi I. We get And we checked the inside parentheses, we get a 1. For any power 1 of 1 is still 1. Okay. But this one, 2 pi I, 2 pi I. 2 pi I. I don't know what that is. Okay, yes, that's okay. Let me check how small this number is. To the e to the negative 4 pi. Okay, so I just checked using the computer. This is approximately 7.157 times. Okay, can you guess what the power will be? Eric, do you have a guess for this power? Amy, what about you? Do you have a guess for this? First, the power will be positive or negative.
Negative.
Because
Did someone
this,
say something?
okay, Eric. Eric wants
Negative 20?
almost. Okay, so I got negative 18.
Bruh.
Why negative 18?
Yes. So, okay, before I answer your question, let me check. Is this a large number or small number?
Very small.
Very, very small.
Very, very, very small. Okay, so this is about 18 zeros before we get to 7. Why is this small? Now you see the power of the exponentials. This is a very large negative number. The exponential of a large negative number will be a very small positive number. Okay. Okay, so this is about the complex numbers. Then we move back to our geometry about the triangles, circles, and the Ptolemy theorem. We start with a circle. Pick 4 points on the circle. Kind of arbitrary. Label them A, B, C, D. We connect the 4 sides. So this ABCD, we call it a cyclic quadrilateral. Okay. We consider a cyclic quadrilateral is arbitrary. Your quadrilateral may be different from mine as long as it's cyclic. Then I connect the opposite side vertices diagonal. Okay. Then this Ptolemy's theorem states that the product of the two diagonals is a summation of the product of the opposite side, ABCD, ADBC, summation of the product, ABCD, ADBC. Okay. For any cyclic quadrilateral, we connect the opposite vertices, get two diagonals. Then the product of the diagonals equals the summation of the products of the opposite side. Okay. We will prove this theorem later, but first, let's state the converse of the Ptolemy theorem. The converse is that if we have this identity for a quadrilateral, then it must be cyclic. If a quadrilateral is kind of an equivalence statement. If we have this assumption being cyclic, then we have this identity. On the other hand, if we have this identity, then it must be cyclic. So being cyclic is equivalent to this identity. Okay, so we will have 5 minutes break. After the break, I will show you how to prove this, why we have this identity. Looks a little bit strange. Okay, 5 minutes break, we'll be back at 8:15. Okay, so to prove this theorem, let's first identify a few angles. I will make a copy of the graph. Let me try to make a copy of this graph. Mm, Copy, paste. Okay. Okay, we start with this AB. This is the chord. Can you find the inscribed angles for chord AB?
AD,
Okay. Uh-huh.
ADB, ACB.
Inscribed angles. Angle ADB, ACB. What can we say about these two angles? Okay, Eric,
They're equal.
why?
Because if we drew the center point O and then we did AOB, then
Hmm?
ADB would be half of AOB and ACB would be half of AOB. So then they're
Okay.
equal.
Okay, so this is our inscribed angle theorem. The inscribed angle theorem. Okay, for convenience, I'm going to label these two angles. I call this, because they are the same, I will give them the same label. Angle one. Okay, someone else. So this is for AB. We move to BC. What are the inscribed angles for the chord BC? Okay, Kira,
BAC and BDC.
we have BAC, BDC, the two inscribed angles. Okay, Kira, what can you say about these two angles?
They're the same.
Why?
They're half of the B. What's the intersection point called? O?
Oh, okay.
Oh,
Oh,
No. So this intersection point is not the center.
oh, okay.
So it's not
Never mind.
needed. We can just
Then
apply
wait,
the,
they're not the same. I don't think. I'm
okay,
forgetting.
what's the inscribed angle theorem? Eric, I know you know.
Huh?
Okay, Eric. The inscribed angle theorem states that for any inscribed angle on this side of the arc, it's half of the central angle. Both equal to the same half of the same angle, so they must be the same.
Oh,
Okay,
what? Yes.
again, I will use IAT for
Oh,
short.
that's what I was trying to say, but I mistook O for the intersection and then got myself confused.
Okay. So we use the center to, maybe I put the center over there because here we have a lot of angles over there. I don't want to put one more point. But if we put a center Then this BAC is half of BOC. BDC is also half of BOC. That's why these two angles equal. Okay, the two angles equal. I'm going to give them a name. I call them angle 2. BAC, angle 2. Because BDC is also the same angle, same measure. We label it 2. Again, same label means equal angles. Okay, somewhere else, we go to CD. What are the inscribed angles for CD? We had Eric, we had Kira. Who's next? Kira, you answered. Okay, someone else. Oh, you have questions? Oh, Kira? No, okay. I will ask Jessica. What are the inscribed angles for this chord CD?
C, CDA,
And
CDB,
CBD.
CBD.
CADCBD. Again, I claim these two angles are the same. Can you tell me why, Jessica?
Because of the theorem.
By the same inscribed angle theorem.
Mhm.
Last chord, AD. Oh, I will label this angle 3. So angle 3. This one is all the same measure, also labeled 3. Okay, and Amy, chord AD, what are the inscribed angles?
There's the one in the center, like it's not labeled. It's in the center to the right. I mean to the
Okay,
left.
give me the vertices.
Oh, AOD.
A, which D? The
Um, A.
inscribed angle, not this angle. This is not an inscribed angle.
Oh, okay. Wait. Okay. Sorry, my sister's a little loud. Can you hear her right now?
No, no.
Okay. Um, yeah, she's being really loud right now.
Okay.
Um, A A B D, I think.
A, B, D. What's another one?
You wrote. Oh yeah. Okay, and then the other one is A C D
A, C, D. Again, I claim they are the same. Can you tell me why?
because they
What
have like the
theorem?
um inscribed angles.
Inscribed angle theorem. For this reason, I'm going to label these two angles angle 4. Angle 4. Angle 4. Okay. Let's recall another theorem. The theorem, if we add this angle and this angle, what do we get? Samuel, do you remember this theorem?
Yeah,
Uh-huh. So what's the angle BAD, angle BCD? What's the summation of the opposite angles
are you
for
asking about the shape or are you just simply want me to do like that? kind of forgot, but like I think
Uh-huh. Okay, do you have a
honestly
guess?
I don't really know.
Okay, Eric answered. Eric is correct.
180
And
degrees.
okay, why?
I don't really know why I just logged
Huh?
my way through. It's because I replaced the inscribed shape with the square and then did that.
Okay. So this follows from the inscribed angle theorem. Okay, if we have, let's go to the previous one. We can see that for this chord, this is half of the central angle. This is half of this central angle. The two central angles give us 360. The half give us 180. Okay, let's use our angle 1, 2, 3, 4. Angle BAD. Angle BAD. Okay, it's angle 2 plus angle 3. We have angle BCD, 1 and 4. So angle 1, maybe I should go to the original order. That's confusing. Okay. Angle 1 plus angle 4. Okay, so again, pi is 180 degrees. Okay, so these are some preparations for the proof. Next, let me make another copy of this. Make a copy. Oh, where are my angle? Okay, my angle not copied. Inconvenient. Let me try to copy it by hand. One, two, four, one, three, four, two, three. Okay, now we have the angles. The next step, we are going to draw a line through this A and parallel to BD. Draw a line L through A and parallel. Okay, let me draw a line through this A. It's about right. Okay. The only requirement we have on this line is that it's through A parallel to BD. Let me ask you, is this line tangent to the circle? Eric can keep nodding, yes or no, why?
I think it's yes.
Okay, so in this setting, it appears that this line is tangent to the circle, but this is just the appearance. It's not always. So note, we don't know and we don't need. Hmm. So sometimes you may use some information that is not there. So here, some of you may say, okay, it's tangent, but we don't have it. Okay. This line is parallel. I will draw a second line. So first step, second step, third step. Draw a line through B with the angle intersecting L at E with angle ABE. Angle 3. I'm going to draw a line I call this point. Okay, it's too crowded. Let's move. Okay, so we draw a line through B such that this angle ABE equals angle 3. This is our construction. I will label this 3. Third line. It's similar. I will draw a line through D. ADF equals angle 2. We draw another line. Get this F angle 2. Okay, so a little bit long. What we did, we start with this line. This line goes through A and parallel to BD. Okay. Second line. Second line, since this angle equals angle 3. Third line. This angle equals angle 2. Now we have this identity. Angle 1, angle 2, angle 3, and angle 4 equals pi. What does it tell us about the two lines, BE and DF? Let me make a copy and we'll go to the next page. Copy. Oh, I have all the angles. Very nice. What we have is angle 1, angle 2, angle 3, angle 4 is pi. I wanted to claim BE parallel to DF. Can some of you tell me why? What theorem did we apply here? Okay, Eric, what's your answer?
Don't you use like the inscribed angle theorem to like find out that 1 plus 2 plus 3 plus 4 equals to 180 degrees?
Uh-huh.
And then since 2 pi equals to 360 degrees, pi is just 180 degrees, so it's equal to pi.
Yes.
And which
Why
BE
this two?
is which
Why?
proves that
Okay, think about it. Think about it. Amy, any reasoning for this one? Okay, it's okay, it's okay. Think about it.
I mean, if we're able to prove that the green line is like, yeah, that's 90, then we would be able
No,
to.
we have no idea what this angle is.
Yeah, I know.
Uh-huh.
So that's why I'm stuck.
Okay. Samuel, any thought on this?
Not really. I mean, it's quite.
Okay, not easy. Eric, maybe Eric on second attempt.
so
It's something we introduced
wait,
at
do we
the very
prove that
beginning. Mhm.
DFA is wait, FDA is
DF
2?
Which one?
FDA
FDA is equals angle 2, yes?
2. Okay. Which means that
Okay, a
Are we
hint.
like overthinking it? If we learned this in the beginning, shouldn't it be
yeah, I
like
probably
really
overthought
straightforward?
this.
Okay, Amy, what's that?
Wait, if we learned this in the beginning, shouldn't it be like really straightforward?
Very straightforward.
Okay.
Okay, one more hint. Euclid. What? Okay,
Can I?
Kira. Mhm.
Is it like the transversal theorem?
Okay, so it's the what's called the Euclid. Which postulate? We
Parallel
have
postulate, fifth one.
fifth one. Yes, the parallel postulate.
Like 1 plus 2 plus 3 plus 4 equals 180, because that's pi.
Uh-huh. So the two
So
lines,
it's parallel.
if the summation of these two angles is less than 180, they intersect in this direction. Bigger than 180 intersect this direction. Equal to 180, they do not intersect we call it parallel. Okay, so this is something we learned in the very beginning. This is the Euclid fifth postulate. Also known as parallel postulate. If the summation of this and two angles is 180, the two lines must be parallel. Okay, this is the big step. What can we say about the quadrilateral B? Okay, goes green color. B, D, F, E. What can we say about this quadrilateral? I want to say it's a parallelogram. Is it? Eric, why not? Okay, what's the argument for not? Okay, let's see where we started with. Our first step,
Never mind, I
draw,
think it is.
okay, draw a line parallel to BD. So we know that EF is parallel to BD. We just proved BE parallel to DF. So this implies so BD. Okay. Since this is a parallelogram, we know that the two sides, the opposite sides, have the same length. Okay, we're almost there for the Ptolemy theorem. Okay, next, I'm going to ask you, what is this angle? Angle. What is this angle? Let's start with angle BAE. Then angle DAF. What can we say about these two angles? BAE, DAF. Okay, Eric.
They add up to be 90.
Well, that's not what we want. The equal to which? BAE equals to angle 1, angle 2, angle 3, angle 4, angle 1 plus angle 2, which is? The information we have is two lines are parallel. Jessica, any thoughts on this? BAE. What can we say about this angle? So Eric, at this moment, we don't need the circle anymore. I will erase the circle to make the graph easier.
BAE
Okay,
is equal to 4
why?
because line L is parallel to BD, and with transversal AB,
Okay, yes.
BAE and ABD are opposite interior angles,
Alternate.
alternate interior angles.
Yes. So since BD parallel to EF with transversal AB. Okay, so I'm going to label this 4. Okay, someone else? DAF. Amy, DAF.
DAF is equal to also, wait, no. DAF is equal to angle 4, I think.
Why? Angle 4.
Also,
Angle 4. Eric used this transversal angle 4, angle 4.
wait, am I looking at the wrong angle?
Angle
Okay,
DAF.
okay. Wait, okay, that angle. That one is equal to angle 1.
Angle 1. Okay, Eric also entered. So this is angle 1. Okay, why?
Because if you like angle 1 and angle DAF are
Mm?
alternate interior angles.
Mm-hmm. For the same
So,
parallel line, what's the transversal?
AAD.
Yes. Okay, next, we will start with this angle, ABE. It has two angles, angle 3, angle 4. Can you find another angle over there with two angles, angle 3 and angle 4? Okay, I'm going to make a copy of this. So we go to the next page. Yeah. It's very easy for me to make a copies, but maybe difficult for you to make a copies. I noticed this. Okay, triangle ABE. This is, oh, it missed my angle 1 and 4. 1 and 4. This angle 1 and 4. Okay, that's good. So ABE, it has two angles, angle 3 and angle 4. Find another one. Okay, which triangle also have these two angles? 3 and 4. We see 3 here, 3 here. Which one works? We need to find angle 4. Angle 4 here, angle 4 there. Okay, Kira,
ADB.
let's check.
Is that what?
A,
Oh, never
B,
mind. Wait. ADC.
ADC. ADC, we see have angle 3, angle 4. Okay, nice. Angle A. Okay, let's match. Which vertex match which? We want to match angle 3 with angle 3. So we match A with B. Angle 4 with angle 4. So triangle A, B, E. We match A, angle 4. Angle 4 is C. And the B for angle 3. Angle 3 is angle A. C, A, D. Okay, so this one for angle 4, C for angle 4, B for angle 3, angle 3. That's how we match the vertices. Okay, two triangles with a pair of equal angles. What can you say about these two triangles? Okay, Eric,
They're similar.
what theorem?
Similar triangles, theorem, angle.
Okay, AA similarity theorem. Okay, that's the first treasure hunt. The second one, we move to angle ADF. ADF, we have 1 and 2. Now, can you find another triangle with angle 1 and angle 2? Another triangle with 1 and 2. Oh, I see A, C, A, D, A, A, D, A, D, F, C, A, B. So C, A, B. We have this angle 1 and angle 2. We start with ABC. Then we match the vertices. Triangle ADF. ADF. A is angle 1. Angle 1 for C. D is angle 2. Angle 2 for A. And we left it with F and C. F and B. Oops. C, A, B. Again, these two triangles, they have a pair of equal angles, so they are similar by the same AA similarity theorem. Okay, two triangles are similar we know that their corresponding sides have the same ratio. Triangle ABE similar to triangle CAD. This implies the corresponding side AB, AC, AE, CD, BE, AD. They have the same ratio. Similarly, triangle ADF, CAB implies the corresponding sides have the same ratio with AD over AC, AF over BC, DF over AB. Okay, the last step. Let's go back and see what we are looking for. We are looking for ABCD, ADBC. I'm going to copy this. We are looking for ABCD, ADBC. If we check the first identities, which one give us ABCD? Okay, Eric.
AB over AC equals to AE over CD. We get ABCD equals to AEAC.
Okay, cross multiplication by this identity. Get ACAE. Oh, they use a different color. Okay, somewhere else. In the second equation, which one give us ADBC? Amy? ADBC.
ADBC is the
So if we check
wait, I
this,
don't
ADBC is equals to,
okay, that's what you're supposed to do.
Hmm.
A AC times A.
is this identity.
I was a little confused.
Okay. Is it clear now?
Yeah.
Okay. Okay, now let's add them together. See what we get. A, B, C, D. A, D, B, C. First one, A, C, A, E. Second one, A, C, A, F. They both have AC. Let's put the common factor out. Live with AE, AF. What's AE plus AF? Go back to our figure. AE, AF. This is just EF. Okay. But what is EF? EF, we go back to check
The line.
because this is a parallelogram. EF is BD. And this completes the proof of the Ptolemy theorem. The summation of the product of the two opposite sides equal to the product of the diagonals. How did we prove it? The key steps, we draw a parallel line, draw two triangles. The key observation is these two triangles similar. These two triangles are similar by looking for the common angles. The common angles, so they are similar. When they are similar, we have this equal ratio. Equal ratio, we do cross multiplication. Then we do addition, we get the result. This is the, you can see the proof is very long, have many steps. And we use all the knowledge we learned before with the inscribed angle theorem. Use this many times. The Euclid's fifth postulate. And we have this AA similarity theorem. And we proved this Ptolemy theorem. Okay. So in this week's homework, we will have some practice about this Ptolemy theorem. Okay. Let me stop recording.